Hi everyone, thank you for your interest in our paper. This is Sangwoon Kwak and Weeyoung Kwon from Electronics and Telecommunications Research Institute and Chung-Ang University. Today we are pleased to present our work, MoRel. To begin with, MoRel is designed for 4D novel view synthesis. It reconstructs a dynamic 4D scene from calibrated multi-view videos and synthesizes novel views that can be rendered in real time. This capability is essential for immersive applications such as VR and AR, 3D displays, telepresence, and interactive visual systems. I will first briefly introduce 3D Gaussian splatting, or 3DGS. 3DGS represents a scene using 3D Gaussians and renders images through splatting. With high reconstruction quality and fast rendering speed, it has become a standard approach for novel view synthesis. As a result, various 4D Gaussian splatting methods have been proposed to model dynamic motion with reasonable quality. This suggests that Gaussian-based representations are also effective for dynamic scene reconstruction. However, most 4DGS benchmarks evaluate only short clips, usually around 150 to 400 frames. In contrast, real-world videos are often much longer and commonly contain several thousand frames or more. So there is a clear gap between benchmark settings and practical long-range scenarios. To handle such long-range videos, existing methods mainly follow two directions: all-at-once training and chunk-based training. All-at-once training optimizes the full video in one canonical space with a single deformation network. However, long sequences often cause memory overflow or underfitting. The second approach is chunk-based training, which divides the video into smaller chunks and trains them separately. This avoids memory overflow and maintains reasonable capacity within each chunk. However, it often produces temporal flickering artifacts at chunk boundaries, which degrades temporal consistency. For long-range evaluation, we newly composed SelfCap-LR based on the original SelfCap dataset. SelfCap-LR exhibits larger motion magnitude and a wider camera baseline than existing benchmarks. This makes it a more challenging benchmark for long-range 4D reconstruction. This figure illustrates the characteristics of SelfCap-LR more clearly. To address these limitations, we propose MoRel. Its core idea is anchor relay-based bidirectional blending, which relays keyframe anchors over time to achieve both bounded memory and smooth temporal transition. Compared with all-at-once training, our method maintains bounded memory usage while preserving higher representation fidelity over long-range sequences. Compared with chunk-based training, it shows a more stable TOF curve and a more continuous temporal profile, indicating better temporal consistency. Our second key idea is progressive windowed training. A naive chunk-wise training of bidirectional deformation causes inter-chunk interference, especially backward contamination. As a result, updating the current chunk can corrupt motion that was already optimized in previous chunks. To address this problem, we divide the training into two stages: progressive window deformation and interframe blending. First, progressive window deformation optimizes only a local window, which prevents interference across chunks. Then interframe blending connects adjacent windows while preserving temporal continuity without inter-chunk corruption. We assign learnable offsets and decay speeds to adjacent keyframe anchors. Then the left anchor is deformed forward, while the right anchor is deformed backward toward the intermediate time step. Finally, the two deformed anchors are blended with learned opacity weights to produce a smooth temporal transition. A simple linear blending often produces blur and ghosting in the transition region. In contrast, our learning-based blending generates sharper and more temporally coherent results. Our fourth key idea is feature variance-guided hierarchical densification, or FHD. First, in variance-based leveling, anchors are grouped into different levels according to their feature variance. This allows us to distinguish low-frequency regions from high-frequency regions. Then in level-wise densification, densification is controlled differently for each level. As a result, low-frequency structures are stabilized first, while high-frequency details are progressively refined later. Based on these key ideas, this slide summarizes the overall architecture of MoRel. MoRel consists of two phases: anchor relay and bidirectional blending. The anchor relay phase builds temporally distributed keyframe anchors, while the bidirectional blending phase connects them smoothly over time. We evaluate MoRel on SelfCap-LR, our long-range multi-view benchmark curated from SelfCap. For evaluation, we use PSNR, SSIM, LPIPS, and TOF, and compare our method with both all-at-once and chunk-based baselines. First, compared with all-at-once methods, MoRel achieves the best overall quantitative performance. This shows that MoRel preserves high representation fidelity while maintaining bounded memory on long-range sequences. Next, compared with chunk-based methods, MoRel also shows superior performance. Conventional chunk-based training often suffers from temporal inconsistency and flickering at chunk boundaries. By contrast, our bidirectional blending produces smoother transitions and better temporal consistency. We further analyze metrics that are particularly important for long-range videos. As shown here, MoRel keeps memory usage bounded through on-demand loading, unlike all-at-once methods. At the same time, it achieves the best TOF, indicating stronger temporal consistency than chunk-based methods. We also compare qualitative results on frames sampled at long intervals in SelfCap-LR. Compared with previous methods, MoRel produces sharper details and more stable appearances over time. These results show that our method preserves both visual fidelity and temporal consistency in long-range scenes. Thank you for listening. Please scan the QR code to visit our project page for more details, including additional results and videos.